Hello everyone, my name is Benson Nagy and I'm an application engineer at Gamax Laboratory Solutions. In this presentation, I would like to share some information on modeling and simulation of electric aircraft architectures for both desktop and real-time simulation. Throughout my presentation, I will use an example of a hybrid electric aircraft. This is a system that was put together that reflects certain technology attributes that are important for this discussion, and it doesn't represent a specific model of an aircraft. Please also note that the techniques we cover in this presentation can be applied to different industry segments as well. For example, we can implement the same modeling guidelines for vehicle development in the automotive industry. Let us take a look at our agenda. I will begin by discussing the relationship between model fidelity and technology readiness. This will help set some context on the choices we make for model fidelity in relationship to where we are in the technology development cycle. Next, I will introduce the Simscape local solver, how it is used, and how it relates to the Simulink global solver. Then give an overview of how we can use different sample times for different portions of a multi-domain physical system model. This is particularly important when considering real-time simulation. I will then discuss the notion of hybrid electric aircraft system in more detail. I have a number of variants that I will discuss, ranging from a DC equivalent system to a system that incorporates thermal response with active cooling on the generation system. Next, I will discuss considerations for making a simulation model real-time compatible and show the results of real-time simulation using Simulink real-time and SpeedGoat hardware. In the end, next to the summary, I will also provide you a link where you can download the models that will be shown in this webinar. In this section, I will discuss the relationship between model fidelity and technology readiness. The Technology Readiness Level Scale, or TRL scale, was originally developed by NASA, and it quantifies the maturity of a given technology at a given stage of development. TRL 1 is your first moment, where you have the initial idea and begin conducting basic research, and TRL 9 is where you have proven in-service technology. The TRL scale is open to some interpretation. In other words, one person's TRL 5 may be another person's TRL 6, but the scales consistently follow key development attributes that you can see on the left. Assigning technology attributes to specific TRL number is typically done by the engineering team who is working on the technology. If we first think in terms of model fidelity for desktop simulation, then we typically see different levels of model fidelity coming in at different technology readiness levels. As you begin basic research, you will have models that are low fidelity. For example, you may have models that have basic functionality in that they come with some high-level system information, such as power flows and component sizing, but which are technology agnostic, meaning the models do not capture specific technology characteristics. As your technology matures, then the simulation models that capture more specific technology attributes will be created. For example, you may incorporate models of actual technology types such as PMSM with field-oriented control, but at the medium fidelity stage, you may still not have vendor-specific information on physical components and control components. A high-fidelity simulation model would have vendor-specific architecture, including parameterization of physical components and control system architectures. The model could also include detailed power electronics, thermal and cooling systems, and communication protocols. Notice that all fidelity levels can track up to TRL 9. The reason for this is the following. As your technology matures, you can develop models with different levels of detail, not only support implementation of your technology, but can also be used for coaching technicians, as an operator training simulator, or as a digital twin. Each of these applications require different levels of model detail. The other view we can take is to explore desktop simulation, real-time testing, and production implementation as a function of technology readiness level. When we look at this view, initial de-risking and feasibility assessment is explored on desktop before moving on to a real-time testing environment where hardware in the loop and rapid control prototyping is conducted to further de-risk control algorithms and physical architectures. The production stage is where algorithms are deployed on actual production hardware, and this is where automatic code generation, which deploys straight to target, can offer significant benefits in verification and validation as you near full system deployment. In this presentation, I will consider only TRL 1 to 4, with only a slight enrichment on TRL 4, as I consider deploying a physical system model on real-time platform without hardware interfacing. I should note that this is my own interpretation of TRL mapping and is for illustrative purposes only. Let's now look at an example of an electromechanical drive and consider how modeling attributes relate to technology readiness. I should note here that this is an illustrative example based on our own judgment and shouldn't be regarded as a strict mapping, but it will provide some context on how modeling detail can evolve as technology readiness evolves. We begin with an ideal electromechanical drive. This is our lowest level of fidelity, where the relationship between voltage and speed and current and torque is defined by a constant proportionality. With this model, we set a DC voltage level using an average value converter with duty cycle input. The duty cycle relates to specific voltage and hence specific speed, and so we need no feedback control for the speed control. With this model, we can set larger time step to achieve fast simulation, but we only gain high-level information on voltage and current, and we have no specific technology characteristics. We can regard this model as TRL1. Next, we can include a more detailed motor. In this case, linear permanent magnet synchronous machine. We include an average value converter, which converts duty cycles directly to voltage waveforms. And so we have not yet introduced power electronic switching. We can now incorporate a more detailed feedback control system. In this case, a field-oriented control for speed control, and so we can perform rapid design iterations. As we have introduced the technology type and have built a more representative control system, we can regard this model as TRL2. Moving on, we can introduce a switch linear converter with full power electronic switching. With this model, we introduce specific PWM switching algorithms and verify that the feedback control system will operate effectively in the presence of switching. We can also take an initial look at the impact of switching harmonics on voltage and current. As we are performing de-risking of the control algorithm and introducing more technology-specific behavior, we can regard this model as TRL3. While this example was fairly basic, I hope it covered some of the model fidelity considerations as technology readiness evolves. Moving on to our next section, I will explain the relationship between the Simscape local solver and the Simulink global solver. And we will also discuss how these settings affect simulation performance and accuracy. By selecting local solver on the Simscape solver configuration block, the Simscape network will be simulated using a fixed step solver, and the Simscape network is presented to Simulink as a discrete system. On the other hand, if local solver is deselected, then the Simscape model is simulated using the global Simulink solver. In a moment, I will show an illustrative example to clarify these points. But first, let us talk about the solver types. There are three different solver types defined: backward Euler, trapezoidal rule, and partitioning. I would highlight the partitioning solver. The partitioning solver converts the entire system of equations for the Simscape network into several smaller sets of switch linear equations that are connected through nonlinear functions and can lead to faster simulation of certain networks. On the other hand, it is important to note that not all networks can be simulated using the partitioning solver. For example, highly nonlinear systems or stiff systems are not appropriate for using the partitioning solver. Now that we talked about the background of the Simscape local solver and the global solvers, let me show you how they work in a model. In this model, I have a simple DC circuit with an ideal switch feeding a resistive load. The switch is controlled through PWM with a carrier frequency of 5 kHz and a modulation wave of 50 Hz. There are two versions of the circuit. The circuit on the left uses the Simulink global solver, and the circuit on the right uses the Simscape local solver. In the comparison of the solver configurations, you can see that we have the Use Local Solver option selected for the circuit on the right, and we are using the partitioning solver in this case. While on the left circuit you can see that we have no local solver selected, therefore it's using the Simulink global solver. Now let's take a look on the global solver configuration parameters. You can see in the configuration parameters that the simulation is set to variable step and discrete. This means that the Simscape model on the left will update using the variable step discrete solver. Despite the name, this is a continuous solver and it can detect zero crossings or discontinuities. Please also notice that the voltage measurement is highlighted D1 on the local solver circuit, meaning it is discrete. And notice on the left that the measurement is highlighted CONT or continuous. Finally, notice that both PWM generators use the Simulink global solver as they are Simulink models, and you can see that the PWM signals are labeled as FIM, which means fixed in minor time step, which is a continuous signal. So what does this all mean? Let's take a look at the PWM signals and the results of the simulation. Let us explore the model behavior via looking at the results. You can see that the global solver accurately captures the pulse as it's configured to detect zero crossings. It means that it can detect very small pulse bits. Now we will take a look at the voltage measurements. The yellow traces the voltage measurement using the local solver, and the blue traces the voltage measurement using the global solver. Notice that we see differences in the voltage measurements, so let's zoom in a bit. You can see that while the voltage response using the global solver, or the blue one, can accurately capture pulse width. However, the voltage response using the local solver, which is marked with yellow, cannot capture a pulse width smaller than the defined step time, which is in this case set to 50 microseconds. Note that engineering judgment is needed here to determine the trade-off between simulation speed and accuracy for a given local solver setting. As a general rule, you can tell that you will need to set the Simscape local solver in order to deploy your system to a real-time system, such as SpeedGoat, for example. Moving on to our next section, we will explore how to configure a model that uses different sample times for different physical network segments. The premise is this. When we are constructing a physical system model that incorporates different physical domains, we recognize the following. A single time across the entire network may not be optimal for efficient execution. For example, if we have an electrothermal system with one sample time, we must set the sample time to accurately capture the fastest dynamics, which would relate to the electrical system in this case. However, thermal time constants are typically much slower than electrical time constants, so we would be oversampling the thermal portions of the model, and this leads to slower simulation speeds. However, we can split the electrical and thermal systems and connect them via Simulink signals, and we can assign separate and more appropriate sample times to each model segment. The example shown here shows us one way in which to split a physical system using thermal ports for illustration. You can see that we are transferring both heat flow and temperature across the boundary in order to balance energy flow. You can set different sample times in the solver configuration blocks, and the physical information between the two networks is managed by rate transition blocks. You see here in this example, left side is sampling at D3, and the right side is sampling at D1. For this example, it is not important which is faster than the other. The point is that we can manage the exchange of information using the rate transition blocks. In this section, we will discuss the DC equivalent system model of the notional hybrid electric aircraft. What you can see here is the high-level system model in Simscape. We have two main turbines, from which power is drawn through electric generators at 2700 volts DC. Also, at the 2700 volt DC level, we have two electric turbines, which are driven from the electric motors and the battery. We then step down from 2700 volt DC to 270 volt DC, where our actuators and cabin load is connected. Moreover, we also have basic command and management functionality. This is what we call a DC equivalent system model, meaning that we are not yet modeling the AC components, and we model the main turbines as ideal rotational speed sources and the electric turbines as ideal torque sources. With this model, we can run very rapid simulations which give us information on high-level operational response. You can see from the simulation parameters on the right that we will simulate 2500 seconds of flight profile with 10 milliseconds sampler time for this model. Before we discuss the simulation results, let us take a closer look at the model, namely the generator design and the energy management system. So in the generator design, you can see that we are using an ideal electromechanical converter for Gen 1, and in fact we are using the ideal converters for all electromechanical systems. The energy management is quite simple as well. In this case, if the electrical system demands more than 1 megawatts of power, the battery will supplement the turbine generators. Notice that this is quite simplistic, but with these settings we can clearly see functional behavior in the simulation. And speaking about the model behavior, let's discuss the simulation results. You can see the generator 1 power, turbine 2 power, and battery power in the figure here. You can see that as the turbine ramps beyond 500 kilowatts, the battery kicks in, holding the generators at 500 kilowatts. And once we drop back below 500 kilowatts, the battery then kicks out because the generators are now below the 500 kilowatt capacity, and so we no longer need the battery. Please remember that we have another turbine and another generator that are pulling equal amounts of power. So you will see the battery power effectively being double, as it's also supplying the other turbine. We can conclude here that from a functional perspective, we are seeing the expected behavior of our model. To sum everything up, we can tell that the DC equivalent system models, where you are using the lowest level of model fidelity, you are able to construct system level architectures, test basic functionality, look at basic energy flows, and make sure your component sizings are appropriate for your system. And those simulations run very fast. This particular model simulates 2500 seconds of flight profile in just 15 seconds. Because of the fast simulation, you are in a position where you can thousands or even tens of thousands of simulation in order to gain a statistical significance over wide operational envelopes. Moving on, we will discuss a model of the notional hybrid electric aircraft that contains AC and DC components, and it uses average value power converters. With this model, we will introduce specific generator and actuator technologies, namely permanent magnet synchronous machines with field-oriented control. The generators use a constant speed drive and are fixed at 400 Hz electrical, with the field-oriented controller maintaining DC voltage. The actuators are variable speed and operate under position control. We have also included more detailed main turbines, which are modeled as Brayton cycle gas turbines. The electric turbines are ideal torque sources in this case. We will discuss the inclusion of thermal response generators in the next section. I will open up the model now and we can take a look in more detail. So in our model, let's take a look first at the Brayton cycle gas turbines. So their model is using gas and thermal domains, as you can see here. We connect the generator to the main shaft of the turbine using a constant speed drive here. The constant speed drive is basic implementation. We have fixed the generator connection on the left at a constant speed source of 200 Hz mechanical, which relates to 400 Hz electrical, as the generators use two full pairs. Power is then transferred to the right side, and here reaction torque is calculated. The two sides are operating at different sample times, indicated by D1 and D2. D1 is the electrical sample time, which in this case is 50 microseconds. And D2 is a slower sample time for the gas turbines, which in this case is 0.5 milliseconds. We use different sample times to reflect the different time constants we have in the different physical systems. We will also see that using different sample times enables us to run this model in real time using Simulink real-time and SpeedGoat hardware. Another point we should note here is the solver configuration for the gas turbine. You can see that we are using backward Euler solver type with 3 nonlinear iterations. The reason for this is the following. Equations for the gas turbines are complex nonlinear equations, so we need to use backward Euler to solve these accurately. On the other hand, in the electrical solver configuration, we will see that we are using the partitioning solver with 1 nonlinear iterations. This is more than adequate for this level of fidelity we have in the AC-DC system on the electrical side, so this is totally fine here. On the electrical system, let's take a look at one of the ailerons, for example the left aileron here. So we go into the PMSM with field-oriented control. Let me open the torque control loop here. So what we can see here is the following. We can recognize the standard configuration for the inner torque loop or inner current loop for field-oriented control system. In this case, we are generating modulation waves using the PWM generator block. You can see that we are using space vector modulation settings here. This is important because we will check that in a moment on the simulation results, and we will expect to see certain characteristics here, which we will look for once we get to the results. So now let's open up the results. Let me open the data inspector here, and let's first take a look at the generator 1 power. First, I would like to note that negative is for supplied power. And what you can see here that the power ramps around 250 kilowatts. In this scenario, I'm ramping the power consumed by the electric turbines, and I have instructed the energy management system so that it uses the battery power when the generators reach 250 kilowatts. So we are seeing expected response here. Note that we have ripples in this area. These are a consequence of the actuator cycling from positive to negative angles. Now let's just look at the turbine power. So we will look at the motor 1 PDC here. We see that the power is ramping up. In this case it ramps up to around 1.2 megawatts of power. So we will leave that up and we will take a look at the battery power as well. So let's take a look at what battery PDC here. You can see that it is marked with blue, and you can see that it is ramping up its power as well. It's going up to about 1.9 megawatts in this particular case. So numbers are a little bit contrived here, but remember, if you are wondering why is the battery power more than the motor, well, it's because there are 2 motors. There is 2 electric turbines, so we are seeing the battery powered as a consequence of that. Alright, so now let's clear those subplets And let's go to the aileron results. We will start with plotting the theta, the actuator angles. We will take a look at the left aileron. Here we see that we are cycling them positive and negative, and that's part of the reason why we are seeing those ripples on the DC voltage we saw first in the results. The other thing we should discuss, speaking about the ailerons, is the duty cycles. You can see them here. I have mentioned that we are looking for a very specific signature on this because we are using space vector modulation. So when I'm zooming in here, you can observe those humps at the amplitudes of these waves, and what this means, this double hump, that's a classic signature of space vector modulation. So again, we are seeing what we expected. So with this, we are verifying the functional correctness at this level of model fidelity. So we are on a good track with our model. Let me now close the model and go back to our presentation. So in this section, we will discuss a model of the notional hybrid electric aircraft that contains thermal generators and active cooling. We first expose thermal ports for the permanent magnet synchronous machines that act as our generators. The ports are HA, HB, and HC for the stator windings, and the HR for the rotor. As we want to run the model circuit at slower sample time than the electrical system, we connect the system via Simulink signals. You can see here that I am transferring heat flow rate and temperature information across the Simulink boundaries in order to balance energy. Also note the rate transition blocks, which manage the transfer of the data across two different sample times. In this case, D3 is the thermal system sample time and D1 is the electrical system sample time. The thermal model of the rotor and stator windings is shown at the top and uses conduction and convection elements. The thermal system was parameterized to show thermal response in only a few seconds of simulation, and it is rather contrived. However, the main purpose is to show the modeling constructs that can be used to create multi-domain physical systems. The active cooling system, shown at the bottom, uses thermal fluid, and if a temperature threshold is exceeded, the pump will activate to circulate the fluid through the pipes and cool the systems. Here we see the thermal response of phase A stator winding in both generator 1 and generator 2. It is important to notice that only generator 1 has active cooling. So we can see here the different response and confirm that the active cooling circuit is functioning as expected. In this case, the active cooling circuit is configured to regulate temperature to 60 degrees of Celsius. As I said before, I have parameterized this system to show a thermal response in only a few seconds of simulation time. A more rigorous development of this model would include more appropriate parameter values, observe the expected thermal time constants as a function of dissipated electrical energy and thermal mass. Moving on to our next section, we will discuss real-time simulation of the notional hybrid electric aircraft using Simulink real-time and SpeedGoat hardware. So what we are going to do is to step through the process you go through to build model and deploy it to SpeedGoat. The first step on the model is to select the real-time tab to build and deploy the model, as you can see highlighted with the red box on the model. Next, in the MATLAB prompt, we can create a Simulink real-time object. So TG equals SLRT, now we have that object in TG. Note that there is various ways in which we can interact with SpeedGoat. In our case, to run the simulation, you just type tg.start. We can also use the task profiler to see the task execution time. So you can see the commands here. I won't continue to read those commands, but you can see here how you would do that and then plot the execution profile. The task profiler lets us use and see the task execution time at different rates. The base rate is the electrical sample time, which is 50 microseconds. Subrate 1 is the sample time associated with the Brayton cycle gas turbines, and subrate 2 is the sample time associated with the generator thermal systems. There are two main things to note here. First, the model section associated with the different sample times have been distributed to different cores. This is known as implicit concurrent execution. I will show on the next slide how the user can explicitly control the cores that are used. Second, the thermal system takes around 2 base rates to execute, and the Brayton cycle gas turbines takes around 3 base rates to execute. This tells us that we would be unable to simulate the full system in real time if we didn't split the sample times across the different model sections, and if we were unable to use slower sample rates for the thermal systems and Brayton cycle gas turbines. For the user to have more control over task partitioning across the multiple cores and to achieve explicit task partitioning, we can use model references. In this example, I have used 3 model references to construct the complete system. You can see we have one model reference for the mechanical system, one for the thermal system, and one for the electrical system. Let us take a look at the separate model references. So let's start with the mechanical system. We have two Brayton cycle gas turbines and we have a power input. The 1/z is needed to avoid algebraic loops here. We continue with the thermal system, so we have a thermal model for the windings, and then we transfer the heat flow out through Simulink signals and we bring the temperature back in. Finally, the electrical system. So you can see we are transferring data in and out of the generators, namely temperature heat flow for the thermal system and power for the Brayton cycle gas turbines. Jumping back to the top level, you can see that the three model references communicate via go-to and from blocks. Now that we have configured our model, we can go into configuration parameters and we can configure tasks and then select enable explicit model partitioning for concurrent behavior. Once we have done that, we can explicitly define periodic tasks. So we define three tasks in this case: task elec for the electrical system, task mech for the mechanical system, and task term for the thermal system. A really important thing to note here is that your fastest rate needs to be set in each block. Let me talk about this in a little bit more detail, like why that is so. So we know that we use different sample times for the domains, for the electrical and mechanical system, for example. Then we use rate transition blocks to transfer the electrical sample time to the mechanical sample time. But across the boundaries of the model references, we are transferring the data at the fastest sample time and then deal with it internally in the model references with rate transition blocks. That is why you need to define the fastest sample time in each block. After the model configuration, we can build and deploy the model from the real-time tab and do what we have done before. We create the SLRT object and then interact with SpeedGoat through that object. We need now take this system and look at the task execution times. At the execution times, we have parity with the last system, so I have actually done it to deflect what was done with the implicit concurrent execution. So you can see now we have the three tasks: task elec, task mech, and task term. So to re-emphasize with those sample times that we are seeing here. Task execution times tell us that we would be unable to simulate the full system in real time if we didn't split the sample times across different model sections. And we were unable to use lower sample rates for the thermal system and Brayton cycle gas turbines. With explicit partitioning, we have further control of using computational resources on the real-time system. And as model complexity develops, we may consider partitioning the model at different locations and including more than one sample time per core. These choices will, of course, be system-specific. And at this point, we have fully prepared our model and it can be successfully deployed to the SpeedGoat hardware. And as I mentioned at the beginning, you can download MATLAB scripts and Simulink models related to this presentation. In the end, I would like to raise your attention that you can find us on the social media, and if you have questions regarding this presentation or you have questions in general, you can reach out to us or you can reach out to me directly on the following contacts. With this, I would like to thank you for your attention and I would like to close this presentation.